today's video, we'll be checking out the gas laws. The gas laws involve looking at different variables that affect how gases behave. And the first law we'll check out is Avogadro's law. The name is familiar, Amedeo Avogadro. And he also came up with one of the gas laws, and this is his gas law. He's going to relate the variable pressure to the variable amount of gas. So we're looking at the pressure, which deals with the collisions of the gas molecules with the walls of a container, and also the number of gas particles that are present. And what Avogadro says is that if pressure is the result of collisions, now these molecules are all colliding with the walls of the container, and every time they collide with a wall and bounce off, they exert a force. Now I do want you to recall that pressure is the result of a force over an area. And so I can actually increase the pressure by increasing the number of collisions. And right now this molecule is going to bounce off that wall, and when it hits, it's going to exert a force. And likewise, when this one hits this wall and bounce off, it's going to exert a force. And it's exerting that force over this area. And the area is the wall of the container. So if I actually add more gas particles in here, as I see down below, there's probably double the number of particles in here, I'm going to see more collisions with the walls of the container. And if I have more collisions with the walls of the container, the gas particles will exert a greater force over the same exact area. If there's a greater force over the same area, my pressure will increase. So the key thing here is that if pressure is the result of collisions, more gas particles simply means more collisions. And more collisions is going to mean more gas pressure. So the kind of summary we're looking at here is if we increase the number of particles, we're going to increase the collisions with the wall of the container, which therefore will also increase the pressure. Now, one of the questions you have to look at also, is this a directly proportional or an inversely proportional relationship? Anytime you have two variables that are increasing, like increase my force, increase my pressure, anytime the variables are both going in the same direction, like up and up, this is considered a direct relationship, or they're considered directly proportional. And likewise, if I remove the number of particles, if the particles go down, the number of particles, then also the force would go down as well, because there's less collisions happening. And just to be clear, this is not pressure, this is particles I'm dealing with here. So this is an example of a directly proportional relationship. Boyle's law is going to look at the two variables, pressure and volume. And in order to look at those two, we're also going to say we're going to have temperature is going to be constant. Alright, so we're going to look at temperature is not going to change, and also the amount of particles is not going to change. So we're just going to key in on what's going to happen to my pressure if I change my volume. So we're looking at increasing and decreasing the volume here. What's going to happen to pressure? One thing you have to understand, again, we're going to be using our formula, pressure equals a force, over an area. Alright, so we're always coming back to that formula when we're using the word pressure. So the one thing we're going to change in this relationship here is the volume. Okay guys, so here we go. Check this out here. We got a picture that shows the same number of particles in each container. There's probably about 10 particles in each container. Okay? The question is, which one has the higher pressure? And if you recall, pressure equals a force divided by an area. Well, they both have the same number of particles. Okay, so particles is not going to be the issue here. The question is, which particles are going to exert a force on the wall of the container more often? Okay, when this guy bounces, he's going to have to take a longer amount of time to find a wall. When this guy bounces, there's going to be a wall right there for him to find. With a smaller volume, I'm going to have more collisions. So I'm going to have a greater force where I have a smaller area. And what that gives me, therefore, is an increase in pressure. So I'm going to increase my pressure by decreasing the volume. So the variables we're looking at here is increased volume. What happens? We have a decrease in pressure, because there's more space for the molecules, the particles to travel before they hit the wall of the container. Likewise, if I decrease the volume and shrink that guy down, this is right here as a good example of decreased volume. If I decrease the volume, what's going to happen is that the pressure will increase because there's less space for the molecules to move around. Collisions would therefore happen more frequently. When we look at whether is this a direct or inverse relationship, if we recall in the past, when I had said this, when the variables both had arrows going in the same direction, either up and up or down and down, that was known as direct. And what you're looking at here is as I increase the volume, that is not happening though. The opposite's happening. My pressure decreases. And that is known as an inverse relationship, or they might be said inversely proportional. So these two variables are not directly related, they're opposite. And opposite are considered inversely related. Okay? So likewise here I have a very big volume. What I end up with is a very low pressure. The opposite is true here. When my volume goes down, my pressure actually goes up. Boyle's law is summed up in a pressure-volume relationship, and it's P1V1 equals P2V2. And it's a way we can calculate the actual volumes, the pressures, in the gases. Boyle's law is actually expressed in the formula P1V1 equals P2V2, that's pressure, volume, and pressure, volume. We're not going to really get into that in this video, but Boyle's law does have some math associated with it, and it's simply this formula right here. And if I was going to graph Boyle's law, it's simply looking like this. It's an inversely proportional graph, kind of almost like a J-shaped in a way, but going down in this direction. Lusak's law is going to look at some variables here, and the variables that we'll look at is going to be pressure and temperature. So what's going to happen to pressure as I change temperature? So we're going to look at an increase in temperature and a decrease in temperature, and what's the result of pressure. I'll say it again. Pressure is simply a force over an area. The one thing we're going to keep constant here is going to be volume. So my area will not change. The only thing that's going to change here is my force. The number of particles, or I said the mass in this case, remains the same also. So I'm not going to introduce any more particles into this container either. All I'm going to use is the same number of particles as I did in Boyle's law as well. So the real question is, what's going to happen to my pressure as the temperature changes? And anytime I mention the word force, you have to think I'm also mentioning the word collisions, colliding with the wall of the container. In this scenario, I have a picture. It's showing, oh my gosh, about 10 particles that are inside this this glass vessel, and I have a thermometer there. And the thermometer shows I'm increasing my temperature from 300 Kelvin to 600 Kelvin, and then beyond that. It's going through the roof of the thermometer in this case. This little meter here is showing where the pressure is. The pressure is presently at 100 kilopascals. When I increase the pressure to 600 Kelvin, you'll notice I've doubled the pressure. I've doubled the temperature, rather. My pressure goes from 100 to 200. The pressure actually doubles as well, too. Okay, and what ends up happening is as you heat the molecules up, they end up moving faster. And as they move faster, they end up colliding with the walls of the container more often. So what we're looking here is that more force, because I end up having more collisions. And likewise, as I increase the temperature quite a bit, the molecules are moving around so fast that they're colliding with the walls of the container more frequently, exerting a force on the walls of the container. So what you're looking at here is nothing more than increased temperature, which causes increased pressure because there's an increased number of collisions with the walls of the container. Likewise, as the vessel could be cooled down, the pressure is also going to decrease because we're looking at less kinetic energy, less motion. The molecules therefore are not colliding with the walls of the container as frequently. Lusak's law is summed up as pressure divided by temperature equals pressure divided by temperature. And we're actually, once again, not going to get into the formulas in this lesson. This lesson is just a quick little introduction to the gas laws. But this is considered a direct relationship. And this is the graph that you typically see from a direct relationship. All right? Direct relationship is going to be going upwards in that direction. All right? Yes, we saw the pressure increased, and so did temperature increased, and that's considered directly related. The last law we're going to look at today is looking at Charles' law, and we're going to check out its effects on volume by heating or cooling the container. So we want to see what happens to the volume of a gas as I heat or cool that gas. We're going to try and keep our pressure constant here, and we're also not going to change the number of molecules either. The number of molecules will stay constant as well, although it's not expressed in writing. What's going on here is that I have a vessel, and the molecules are at a temperature of negative 65 degrees Celsius, and that temperature they're actually moving around a little slowly. This is an expandable container, and this is free to go up or down. So it's a wall that can actually move as the molecules increase and decrease in temperature. And what we're looking at here is that as I increase the temperature, the molecules are simply moving around more rapidly. The pressure on this remains the same, and so what happens is that it ends up expanding the gas. Alright, the gas will get turned to a larger volume of gas as it heats up. The pressure is not increasing because this is an expandable or movable wall. Once again, let's check out the variables. As temperature decreases, no surprise, the volume of a gas will also decrease. It condenses in size, it shrinks down. And likewise, as something is heated, it's not too big of a surprise, it's going to expand in size. So Charles' law is simply another directly related relationship here between these two variables. Okay, guys, that's the gas laws in a nutshell, okay? Hope it was helpful. If you're interested in the formulas and using the formulas, once again, tune in, down the road here. We'll have some more lessons on that too. Thanks for tuning in tonight. Have a good day.